It's my pleasure to be here. Thank you for the opportunity and the invitation to present Biohalo, a startup from Copenhagen and a spin-out of the Technical University of Denmark. And we are a spin-out from a big project that lasted for years at the university, trying to establish an artificial fluorine metabolism at the core of this technology. And you might wonder, how does that go together with today presenting a PFAS replacement? And the interesting fact is, if you are able to incorporate fluorine at a very low degree into biopolymers, these biopolymers have very different properties, and they can be similar to PFAS in a range of applications. And let me introduce you a bit more later to that. You have heard a lot about the problem. I just want to kind of say, beyond this healthcare and environmental problems, there's also this production problem. And switching to a more biotech-based one can help there to a certain degree. When it comes to our team, Biohalo is led by two scientists, Nicolas Klink and Mariella Mezzina, who have been developing this technology at the university for quite some years. Looking at our technology to share a few more insight, we engineered a microorganism to be able to incorporate fluorine from an input into a central metabolite. And the central metabolite can then be kind of converted into a monomer. And these monomers can be used to produce a range of polymers. And so we can kind of do the polymerization or condensation of these monomers inside or outside of the cells, and by the molecular weight, for example, can play with the properties of these monomer or polymers at the end. When you compare traditional fluorochemical production practice versus biotechnological production, you of course use much less energy. You can use renewable carbon feedstocks. You have lower emissions because it's done by enzymes and they are very stereoselective, right? You really can avoid that you generate pollutants or any other byproducts. And more specifically, you can have a controlled fluorination. So you really are in charge of what's happening there. So far, we have developed two products that we are pioneering at the moment. The first one is a fluorinated version of PHB. So we have a version of this bioplastic which has in around, let's say, every 50th monomer monofluorination. And this polymer then has water repellency and oil repellency properties with similar water contact angle, for example, to PTFE. And we produce this polymer completely inside the cell and then extract it and try at the moment to develop with various partners coating solutions with that. The second one is that we use the technology that we have developed based on enzymes to also produce other types of products, and that's the 2-fluoromerconic acid that we can produce, which is like a platform chemical which you can use to produce various other things of. And one thing that is quite obvious that you can produce if you're a chemist is a fluorinated version of nylon, and that has also some interesting properties. When it comes to our go-to-market strategy, we really want to focus on the coatings and film sector, and we see a lot of interest from the electronic space, maybe the membrane space, but also from the construction area. Coming a bit to what we have achieved so far as a startup in the space, and I can tell you there are not too many startups, unluckily for us. We won the startup prize at the JEC World Composite Show in Paris last year, and going there in a few weeks already. So if you are also in Paris, let me know. We won some startup prizes in the synthetic biology space. It was really unheard of that you can kind of create this artificial fluorine metabolism because of the strength of the carbon-fluorine bond, which is usually making it a bit unattractive as a metabolite. And then we won some investment prize and got some money. Our main funding source is the Bioinnovation Institute, which is like an incubator funded by the Novo Nordisk Foundation, but we also were part of some very nice programs from EY in the Nordics, from the Innovation Network Advanced Materials. I don't know if you know that. They have a very nice program for startups developing cutting-edge technology in the material space, and also by plug and play. Thank you so much for your attention. I hope could share some positive news that there are, for certain applications, alternatives at the horizon. Thank you.
Thank you so much. We have a few minutes for questions now, so if anyone has any questions, one of you to start.
What limits your degree of fluorination to 1 in 50?
Sorry?
Why when you fluorinate, why is it only 1 in 50? What's the challenge in getting that higher?
It's not so much the challenge, it's what you need.
Okay.
So what we see is that you get a lot of properties already with a very low degree of fluorination, like water repellency or repellency. The only thing that we really see changes a lot if you increase the fluorine content more is the thermostability. And then you cannot stop with, let's say, 1 in 20. You need to go much higher to go to thermostability. This is comparable to certain PFAS. So at the moment, we are looking more in the direction of using the polymers and in other applications.
I think you said that you're currently looking at focusing on films and coatings. Do you expect that this sort of chemistry would also be suitable to other application types?
Yes, what we are focusing on coatings is mostly because as a biotech startup, it's a bit difficult to scale, so we cannot produce 10,000 tons a year in 2 years. So it's more that you need to get the bioreactors running. In coatings, you have and with the companies that we are talking, you have a very, let's say, limited material need, so you don't need hundreds of tons, you need a few tons and have a decent margin. So that's for us the most attractive beachhead market. But certainly when we talk with investors and with other companies, there's certainly also a case for other markets, but they are maybe not our beachhead markets for that reason.
Great. Well, thank you so much.